Good morning, everybody. It is the 26th. It is 9:30 in the morning, and we are going to do some chemistry today. Now, before anything else, I have a couple of announcements. Um, One of them is I actually have some appointments this upcoming week. So not today, obviously, but next Monday and Wednesday, I will not be holding our synchronous class. Um, Instead, what I'm going to do is post what's known as it's called an ed puzzle. Um, and basically, it's a way of taking a pre-recorded lecture and throwing some questions in there. So you watch the lecture, and then there are some questions, just like we do um, typically with our poll questions. Um, but and actually, let me go ahead. Yeah. So ultimately, what that means for you guys is we will not have our class meeting this Monday, which is the third. Yep, Monday the third. Um, so I'm going to say no synchronous class meeting Monday the third or Wednesday the fifth. Um, some of y'all might hear that and think, so does that mean we kind of have like 2 weeks of spring break? If you want to look at it that way, you're more than welcome to. Um, Now, with that in mind, what I'm going to assign is an ed puzzle, is what it's called. It is an assignment that you guys will do, and this is going to be in place of um, some of your other work items. So this will be something that you watch, watch lecture, and answer questions. So these 2 days are going to be asynchronous. Um, oh, am I recording yet? Yes, I am. Good. So with those 2 days being asynchronous, I am going to be posting them as early as possible. I believe that Monday the 3rd, that will be up this evening at 11 p.m. or so. And then I'm getting some great questions in the chat, and I'm going to share them and answer them for everyone in just a second. And then the one for Wednesday the 5th, that will be up shortly thereafter. So hopefully that will be up before tomorrow night. Now, with that said, some of the questions that I got in the chat, one of them was, we will still have quizzes and activities. Okay. One, the activities for next week, assignments or activities number 11 and 12, those are up and you can do those, but you can't submit them yet. You'll be able to submit them as early as Monday, the 3rd. Then for quizzes, so activities, yes, you will still have 2 activities. For quizzes, let me take another look at these real quick. These would be quizzes. Yes, you will still have quizzes. Um, and those will go up. Yeah. So 2 activities and 3 quizzes. The difference is that since this is the week before spring break, what I'm going to have as your due date for all of these items is these are due March 16th. March 16th, which is the Sunday at the end of the week of spring break at 11 p.m. Now, I got a follow-up, or I got another question. Do I want the ed puzzles done at the time of our class or just by the end of that day? Well, the ed puzzles are also due March 16th at 11 p.m. So you have some leeway and you have some kind of flexibility. If you want to go ahead and if you're thinking like, okay, well, I want to get to them, but I don't want to do them kind of too early. Um, oh, okay, for the reason for lack of students in Zoom is because Zoom is dysfunctioning, taking excessive time to load and ending with an error from the group. That is so strange. Let's see. Do I have anything to? Okay, I'm gonna look at participants. Okay. Okay. So it looks like. Thank you for letting me know. That's I don't know what's going on. I'm going to stop my share though because I've had this issue where I will be sharing and then about halfway through class someone will be like, "Hey, are you not halfway through class, but like 5 minutes into class they'll be like, "Hey, do you have any thing that you're sharing on the screen?" Um okay. So I'm going to go ahead and share my screen again. Um if the person who just sent me the message about Zoom dysfunctioning, maybe pass on to those folks to contact ITAC, and call or email them and just say, hey, something funky is going on. Because it might be a campus-wide thing. Okay, so basically what you've got is we've got these items scheduled for Monday and Wednesday, the 3rd and the 5th, um, and they are due the 16th. Before spring break, your practice exam, number two, will be up. And then I'm sorry, I also want to add this other item. The conflict is really just the times that we have our class, Monday and Wednesday. If you would like to meet with me during office hours, uh, I just need you to let me know. Um, and if you want to meet during our regularly scheduled office hours of 12:30 to 1:30, just shoot me an email and say, hey, I've gone through the ed puzzles, I've done all the quizzes, but I'm still kind of struggling with this. And I have no problem kind of jumping onto an office hour and helping you out with that. I don't want you to think like, oh, he's going to Portugal for 2 weeks. I assure you, I'm not going to Portugal for 2 weeks. If you meet me in office hours, you will see the exact same green background that you see right now as you will see during office hours. And this green background. Yeah. Anyway, so I just have conflicts during these times, and it just so happens that it's the 3rd and the 5th. So at any rate, if you have any questions, anything comes up, please let me know. And I'm glad to jump into office hours. I'm glad to meet with you at any other time. Just let me know and we can figure something out. Okay, so what we're going to be doing today is we are going to be looking at molecules that do not have lone pairs of electrons, and specifically lone pairs of electrons on their central elements and central atoms. Um, if you've ever taken a chemistry class before, or if you remember back to whenever you took maybe I know this was the chemistry class that I took as in high school. It was integrated physics and chemistry. IPC was what it was called. Um, I kind of felt like I was getting into chemistry whenever we were drawing molecules. And so far we've done a couple of different things. Um, we have looked at valence electrons. I feel like I've said valence electrons a large number of times. Um, For activity number, I got a private message. For activity number 10, are we supposed to draw the Lewis structure? Just wanted to be sure. Um, yes. Yes, you are. Um, okay, so we're going to be working on basically drawing these molecules, and this is going to help you, kind of understand what molecules look like and what's the relevance, what's the importance of these valence electrons. So, first and foremost, this captures kind of the main group elements that we talked quite a bit about. Um, I think that it's good to look at this and then to also look back at the periodic table. If there was a portion of this that I would say is maybe more important than any other portion, I would say these and pretty much these. Those elements right there are the ones that you probably want to have the most kind of comfort with, like recalling and be able to recall them as quickly as possible. These are the Lewis structures for these individual atoms. What we want to do is take an atom, go from drawing an atom to drawing a molecule. Now, we've looked at some molecules before. I've shown you structures of molecules before, but now we're going to go through what is the deliberate process? What are the steps that we need to follow in order to draw a molecule? So, anytime you're confronted with a molecule and the formula, so like let's go with CH4 as an example. There's our formula. We want to take that formula and we want to convert it to a structure. And we want to see kind of where are these atoms with respect to one another. Does CH4 look like this? Does it look like this? There's a number of different ways that you could kind of throw these atoms around and come up with a structure. Now, I'm guessing that if I said, hey, this is the structure of CH4, give me a thumbs up if you agree, or go with a thumbs down or an N if you disagree. Add it to the chat. Yep, getting lots of N's, lots of no's. And you're absolutely right. Why is that structure that I just put together? Why is that a garbage structure? I mean, no disrespect to those letters, but that's a kind of a garbage structure because we've talked about covalent bonds. We've talked about sharing of electrons. And this right here, that arrow, I pointed to a line. What does that line represent? Spoiler, it's on this slide. Two electrons. It represents a bond, absolutely. That bond represents two electrons. And okay, so that's two electrons, that's two electrons. Okay, so arguably this hydrogen then has four electrons around it. No, hydrogen doesn't like to have four electrons. Hydrogen likes to have two electrons. It likes to bring its own and then share one. That's what hydrogen likes to do. And do we ever like making hydrogen angry? No, because hydrogen, like the Incredible Hulk, when it gets angry, you don't want to be around. Okay, so that's the point that I'm getting at. We want to be able to take this formula right here and convert it to a structure. We want to position all of the atoms properly to come up with, well, what does this thing actually look like? Or, theoretically, what does it look like? So here's our process. Our process is after you've identified all of the atoms and all of their electrons, you need to find the central atom. And whenever I say all of their electrons, do you think I'm talking about total number or valence? If you think I'm talking about total number, add a T to the chat. If you think I'm talking about valence electrons, add a V to the chat. Okay, I'm getting lots of T's. I'm happy that you guys are saying this. In this case, when we are talking about bonding, we're actually only talking about valence electrons. So this is kind of funky, and I'm sorry to, have any sort of misleading language here, but let me go ahead and add this in. All of their valence electrons. Because when it comes to bonding, the valence electrons are the ones that matter. Okay, so I'm happy that we cleared that up, that valence electrons are the ones that we care about. So what we need to do, our first step, is to get the sum of valence electrons. So when we talk about drawing a structure, we need to be able to reference and kind of recall this table right here and add up the total number of valence electrons that each atom brings. So if we were, for example, looking at this structure or this right here, CH4, how many valence electrons does carbon bring to the table? Does anyone know that off the top of their head? Add it to the chat. 4. Carbon's rolling in with 4 valence electrons. Absolutely. Okay, carbon's bringing 4 valence electrons. I did not, let me extend my circle there. Okay, so here's carbon and its 4 valence electrons. Okay, now we've got 4 hydrogens. If we're getting the sum of valence electrons, so that means all of the valence electrons from all of the atoms, each hydrogen is bringing in 1 valence electron. Add a Y or a thumbs up to the chat if you agree with that. Okay, okay. Now, do you think that we say, oh, well, +1? Or do you think that we say +4 if we're trying to come up with the total number of valence electrons for this structure? Do you think that we're looking for 5 or do you think that we're saying +4? I'm seeing +4, then I'm seeing a 4. You're absolutely right. Because we don't just say, oh, well, sure, there's 4 hydrogens, but we only count 1. We account for every single hydrogen atom and the electron, the valence electron that it's bringing in. So if we're drawing the structure for CH4, how many electrons are we going to be able to work with in drawing this structure? And how many electrons is how many valence electrons? Add it to the chat, the sum of our valence electrons. 8. You're absolutely right. We've got 8 valence electrons that we can draw. Okay, so that's going to be something that we just kind of hold off to the side. And I'm going to work through these steps here. So after we have all of our atoms, check, and all of their valence electrons, check, find the central atom. Okay, there's a little bit of a, a rule that you can follow. Your central atom is typically going to be the first element that's listed in the formula. So for CH4, carbon is the first element that's listed. We're going to pick that as our central atom. And then what we're going to do is we're going to draw all of the other atoms surrounding that central atom. So basically it's like this, X, Y, 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 Y. Okay. Then we're going to draw a line to connect. Boom, boom, boom. Then we're going to place all other electrons until we reached our total. And whenever I'm saying total here, I'm still talking about valence electrons. So I want you to, and I don't want to like deceive or confuse you, but whenever we're talking about bonding, just keep in mind we're always talking about valence electrons because valence electrons are those outermost electrons that can be shared. Inner electrons, those core electrons, they're not going to be shared. And so when we talk about bonding and whenever I say like, oh, the total number of electrons, just keep in mind that context of, oh, he's talking about bonding. So we're talking about valence electrons. Okay. After we've placed all of the electrons, all of the total valence electrons, we try to get each element to have a complete octet. And then if we need to, we'll add a double or a triple bond. Okay. Can I get a let's go with the letter X in the chat if you're ready to go and ready to move on from here. Okay. Okay. Let's do it. I saw somebody put a capital X in, so that means they are capital ready to go. Okay. So this table, I think that you guys have a good understanding of this information, but not necessarily displayed in this way. Because we've talked about the periodic table and we've identified the groups. And you know that whenever you look at the periodic table, you might see 18, 17, 16, 15, 14, 13. Okay. Those are the groups in the periodic table, but you'll also see sometimes these listed as 4, 5, 6, 7, and then your noble gases. The second number here indicates the number of valence electrons that these atoms have. And we talked about kind of what atoms like to do. Do they like to pick up an electron? Do they like to lose an electron? They like to reach 8 valence electrons or 8 electrons by sharing. Okay, so I'm going to use this slide and I'm going to go back and forth from this slide and to our working slides a couple of different times. So I apologize in advance if it's like, whoa, whoa, whoa. And can I get if anyone currently does not see anything on the screen, please send me a private message. Um, just, I want to make sure that everyone can see that I am writing something on the PowerPoint. Okay, now next up, CH4. Let's draw it. CH4 is a substance commonly known as methane. It is an organic compound. It's arguably one of your simplest organic compounds. Methane is a great contributor to um, what? Sorry, I blanked for just a second. Methane, CH4, is a big deal. Methane is something that cows produce a lot of as a waste product, and well, it kind of it can smell. It's a volatile gas. It can light on fire. Methane, CH4. What we want to do is go back to the information that we had just a second ago. How many valence electrons? What was our total number of valence electrons that we had for methane or for CH4? 8. Perfect. Thank you very much. And then our central atom, in this case, carbon, is written first. And we got hydrogen, 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 hydrogen. And I might have done that out of order. Maybe I should have placed the H's and then drawn the lines. But with this structure that I've drawn right here, how many electrons have I drawn? How many electrons are represented in this structure? 8. Okay. When you look at a hydrogen, let's just I'll pick out this hydrogen right here. How many electrons are kind of around that hydrogen? 2. Okay. How many electrons does hydrogen like to have? Okay. Hydrogen brings in 1 electron, but hydrogen likes to get to 2. Hydrogen's octet is 2 electrons. So it likes to have one because it brings its own to the party, but then it likes to share another electron. So hydrogen reaches its octet with 2 electrons. And it's happy. Okay. So hydrogen is an example of an element that doesn't need to have 8 electrons around it. Its octet is 2 electrons. Now I know that's a little bit confusing because oct means 8, but that's what hydrogen likes to do. It likes to share 1 electron and bring its own, so then it gets to 2 electrons. Now, carbon rolls in with 4 valence electrons. It likes to share electrons. How many electrons are will complete carbon's octet. Okay, four more because it's bringing four of its own and then it's going to share four more. So then it has a total of eight electrons around it. Does that make sense? Can I get a Y or a thumbs up for yes, that makes sense? If it doesn't make sense, you can send me a private message. Okay. Now, when we look at this structure right here, um, I'm going to erase this. I'm going to make a bigger circle around this hydrogen and ask the question, is this hydrogen happy? And can I get a Y or a thumbs up in the chat if you think that this hydrogen is happy? Yeah, sure. I like it. That works. It has its two electrons. It's good to go. Now, carbon here. I'm going to draw a circle around carbon and all of the bonds that it's using. Is this carbon good to go? Is it happy? Yeah. Okay. Now, with that said, I've satisfied the octet of both the hydrogen and the carbon. And how many electrons did I draw? Here's two, 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 two. I drew eight. And you know what? I had eight to draw. How does hydrogen have two electrons? That's a great question. Hydrogen has two electrons by one bringing its own, because if you remember hydrogen on the periodic table, actually, I'll go back. Hydrogen right here. Think about it as it owns one electron. Now, what it likes to do is it likes to grab another electron by sharing it. By sharing, hydrogen likes to share another electron. And you know what? That gets it to have the same electron configuration as its nearest noble gas of helium with two electrons. Does that make sense? Because we talked about, okay, I got the person who asked me that question responded with, okay. It might be helpful to draw the structure with the dots and then, okay, that sounds good. I'd love that. Thank you very much. So think about this as we've got carbon. And then hydrogen. And I see another question in the chat. I'm going to get to that in just a second. So this hydrogen right here has its own electron. This carbon has four electrons. And what I'm going to do is move this hydrogen right here. I'm going to do that. This hydrogen right here. Do that. And this one right here. Okay, now I'm going to erase all my arrows that I just drew. Does that help clarify? Okay, thank you very much for one of your classmates suggested that I do that, and I thank you very much. I got a private message of how do I know what the octet is for each element? That is a fantastic question. So your octet, think about it as every element wants to get to eight electrons, eight valence electrons. If we think about fluorine, the elemental fluorine, remember that term elemental fluorine or elemental something? Elemental means that it's neutral. Now, fluorine here has seven valence electrons. Okay. Its neighbor, neon, has eight valence electrons. These noble gases are stable. They have complete octets. So they have eight electrons surrounding them. Fluorine, what it's going to do is it's going to be able to pick up an electron, in which case It's not going to be elemental, but instead it's going to have an F minus one, a negative, because it picked up an extra electron. Now, what does that look like? Okay. So this molecule or this variation of fluorine has a minus one charge. For just a moment, ignore the charge. How many valence electrons? I had to stop because I got a fantastic question in the chat. This fluorine has the same electron configuration as neon. Okay. Um, so your total electrons is just adding all the electrons from my total electrons is yes, it's adding all my electrons from all of those elements, all of my valence electrons. And then I got a follow-up question of so fluorine and hydrogen go well together. Yes. Hydrogen and fluorine. Think about it as so fluorine, boom, 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 boom. I'm going to draw its 7 electrons. And now I'm going to switch colors. I'm going to go with blue. I'm going to draw a blue electron for hydrogen. HF. Hydrogen loves to pair up with fluorine because, well, they both get something out of the equation. Now, I'll give you another example of a compound that we will draw in a couple of days, or we'll look at in another way. Water. Now I'm going to switch colors again so I can draw my hydrogens. We've got this right here. Add to the chat if you know what this is. What is that referred to as? Give you a hint. It starts with a L and ends with an lone pair. That's right, a lone pair. Sorry, that's my bad dumb joke. Okay, that's a lone pair of electrons. Okay, now I got some private message. So in CH4, is H negatively charged or no because it is its own molecule? Um, okay, so in CH4, if we were to calculate a charge from that, um, the charge on that hydrogen would be the hydrogen is almost always going to be a positive charge. Um, it is, but don't look at that hydrogen and think, oh, it has to have a charge because it's a part of that molecule. So gold doesn't like to pair with fluorine, correct? Um, yeah, that's fairly true. No, no, no. I got a private message that was so gold doesn't like to pair with fluorine, correct? Because it would make it off balance. Yeah, that's a very reasonable way of looking at it. Okay, so can I get a thumbs up or some response in the chat that we're good with drawing CH4? Okay. Okay, great. Great. Okay. So now we're gonna, like I said, look at this chart again, but we're gonna go ahead and jump on forward. So are we going to draw one at some point? One what? A molecule on an exam? You will not be drawing molecules on your exams. They are a part of your activities, though. So you'll have the practice there. Alternatively, drawing I think drawing compounds is helpful, you know, just through the practice of okay, you have to go through the steps. Okay, so let me jump to yeah. Oh, sorry about that, everyone. Um, okay, so what we've done is we've looked at CH4. Now, if I were to say try to draw another molecule, um, And in this case, what we're going to do is we are going to draw SF6. Now, what I want you to do is look at this right here. And I'm going to give you a little bit of a hint. Draw an arrow here, and draw an arrow here. Is anyone familiar with the field of organic chemistry? Or have you heard of organic chemistry? Okay. So organic chemistry is a field in which um, you're dealing with carbon-based molecules. So carbon-based molecules, I'll say carbon-based compounds. Okay, so carbon-based compounds. Now, as a follow-up to that, um, can anyone think of a carbon-based compound or carbon-based substance? If you can either add it to the chat or kind of keep it in your head. Um, I'll give you an example. Let's see. Let's see, what do I have around here? Oh, oh yeah, paper. Carbon dioxide is absolutely carbon-based. Paper here. Does anyone know what paper is made of? Trees. But does anyone know the substance from a tree or from a leaf or something that is carbon-based? It is a sugar called cellulose. And this is not information that I'm going to be testing you over or anything of that nature. But what I'm getting at is there's, I don't know if I would say almost everything, but the abundance or the number of substances that you encounter in any given day that are carbon based is an absolutely huge number. So, whenever people talk about or work as biochemist, chemist, organic chemist, they're dealing with things that are very carbon based or carbon centric. Now, I've kind of drawn these lines to indicate exceptions to the octet. The octet rule is that an element or an atom wants to get to 8 electrons around it. That's why oxygen likes to share 2 electrons, because if it can share 2 electrons, boom, boom, can share 2 and it gets to 8 by sharing. Now, carbon likes to share 4. There are, however, some substances and some elements that can break the octet. Boron, for example. Well, boron doesn't need to have a total of 8 electrons around it. And then phosphorus over here, and anything beyond phosphorus can have more than 8. So less than 8, more than 8. Okay, so I bring these up just because this is kind of well, it's a good contrast. Now, SF6 here. What we need to do with this is we need to, well, get our total number of valence electrons. I'm going to give you a second, and I'm going to do it myself. Um, Go ahead and put together the total number of valence electrons for SF6. And whenever you're ready, add it to the chat. Ooh, ooh, live it up. Live it up. Got a couple of private messages from folks who came up with 48. You're absolutely right. I'm going to resume my share here. Here's what I got. A sulfur atom brings in 6 valence electrons, and each of those fluorine atoms brings in 7 valence electrons. So 6 times 1, 7 times 6, that brings us to a total of 48 electrons. Now, the question was, what is our total number of valence electrons? Total. Okay, so we got 48. Now, my next question, which is our central atom? Sulfur. Sulfur is my central atom. Okay, now I want to draw the Lewis structure for sulfur. That's not supposed to be an exclamation mark. That's supposed to be lone pair of electrons. Okay, so there's sulfur, and then fluorine looks a little bit like this. So I got these numbers from this slide right here. So this shows, sorry, actually, you know what I'm gonna do? I'm gonna go over here. This table shows me my total number of valence electrons. Fluorine, all of those dots, each one of those dots represents a valence electron. So there's a total of 7 dots surrounding that fluorine. And then sulfur, each one of those dots represents a valence electron as well. So there's 7 dots around fluorine and 6 dots around sulfur. That's where the 7 and the 6 come from. Then, if we go back over here, this is my formula for this compound, SF6. This is, and actually, you know what? There's a bonus point on your next exam if someone who can tell me what the name of this compound is without Googling it or anything of that nature. Okay. Add it to the chat. You can send a private message if you want. I'm going to go ahead and proceed though. We've got our 1 sulfur and our hex, our 6. Oh, live it up. Live it up. Good job, everyone. Marking that on my paper. 1310. E2, bonus point. Great job. Sulfur hexafluoride. So this is sulfur hexafluoride. We've got 48 valence electrons. We've got a sulfur in the middle, and then we've got 6 fluorides. Okay, now I'm going to go ahead and do this right here. It's really tempting to see this and say, oh, okay, well, I should start drawing all of these electrons. It's not what we want to do. What's our process? After we've identified our central atom, what's our next step? Our next step is to draw all of the other atoms around that central atom. Another way to put that is write the letters 3, 4, 5, 6. 6 fluorines. Then what I want to do is draw a line between sulfur and each one of the fluorines. Okay. Now, with that in mind, tell me in the chat how many electrons are currently surrounding sulfur. 12. Okay, I got a point of I need double bonds. Okay. 12 is correct because each one of those 6 bonds represents 2 electrons. I've got 6 bonds, 6 times 2, 12. Now, someone proposed that we need double bonds. We don't necessarily want to do that. If you rem One important point is that sulfur is an atom that can exceed the octet. So that means that it can have more than 8 electrons surrounding it. So with that, is sulfur having 12 electrons, is that a bad thing? Or is that a problem? I mean, it can exceed. Absolutely right. It is not a problem. Okay. So that right there, this where I started, or where I am right now, that's not a problem. It might look a little funky compared to CH4, but it's not a problem. Now, do we need multiple bonds? Do we need a double or a triple bond? Let's not go there quite yet, because what we want to do is we want to look at the electrons that we've drawn, and then we kind of want to do some accounting. And if there is anyone in this class who is an accounting major, um, I'm probably going to grossly misuse terminology, and I apologize. Yeah, I apologize. So we have 48 valence electrons. Actually, I can move a little closer to that. We have 48 valence electrons that we can work with. How many have we currently drawn? 12. So we want to take those 12 and subtract from the total number that we have, which leaves us with how many electrons to possibly draw. 48 valence electrons minus 12 gives us ba -ba -da -ba 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 -ba. I got a 36. Okay, somebody asked me, how did I get 12? Don't worry. The 12 came from the total number of electrons that I've drawn as single bonds. Each one of these bonds represents 2 electrons. I've drawn 6 bonds. So I did, I'll write this out over here. 6 bonds, 1 bond equals 2 electrons. So 6 times 2 equals 12. Great question. Okay, so now I got to erase this though, because I'm really bad at playing. Okay, I'm going to move over here. And I'm sorry that my S looks like a backwards number 2. Um, I have no one to blame for that but myself. Okay, so there's my SF6. Now what I want to do is I want to complete the octet of all of my surrounding electrons, or all of my surrounding atoms. So I'm going to go ahead and switch colors. I'm going to go with blue. And is there some sort of magic code to switching to blue? No, there's not. What I'm going to do is I'm going to put 1, 2, 3, 4, 5, 6. Okay. So I put 6 electrons. Why did I put 6 electrons? I put 6 electrons there because one thing, if we look at fluorine, how many electrons are around or are surrounding fluorine in that circle? 8. I've got 8 electrons there. So my question for you is, does fluorine have a happy or a satisfied octet? Yes, it does. So fluorine's good to go. Now, I'm going to go ahead and, just to be specific with this, I'm going to say minus 6. Now I have 30 electrons left to draw. Now, somebody sent me a message of, is it 36 divided by 6? Yes, it is, but I just want you to go through the process of drawing each one of these, or all of these electrons. Okay, so I'm going to put a check mark up here. That fluorine is good. Now this fluorine looks exactly like the other one. I've placed 6 electrons. That fluorine has a satisfied octet. So I'm going to say minus 6. 24 electrons left to draw. 1, 2, 3, 4, 5, 6. I'm not going to circle that one because I think that you guys are probably getting the point. Where each one of these fluorines, well, now I've minus 6, 18. Minus 6, 12. Okay, that's a 12. 12 minus, boom, 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 boom. Minus 6 is 6. And then last but not least, this other fluorine right here. minus 6 equals 0. Okay. Do we have any electrons left to draw? Add it to the chat. No, we don't. So is our structure of SF6, is it good? Yeah. And I wasn't saying that like, what do you guys think? From all of the times that you've seen the structure of sulfur hexafluoride, does this look like what you've seen before? I was really kind of getting at, did we go through our process? Did we get our sum of our valence electrons? Yes, we did. 48. Did we identify our central atom? Yes, we did. Sulfur. Did we draw lines representing two electrons or representing a bond going from sulfur to each one of the adjacent atoms? Yes, we did. Sulfur. Did it exceed the octet? It did. Is that a problem? No. The most common culprits or the most common elements that you guys are going to see that exceed the octet are phosphorus, sulfur, and chlorine. Those three. You're going to see those three exceed the octet almost more than anything else. And you're going to see boron have less than a complete octet. So we went through the process. Then we started placing 6 electrons around each one of our fluorines. Why did we do that? Because fluorine wants a complete octet. It wants to have 8 electrons around it. Fluorine doesn't exceed the octet. Fluorine's like fluorine, oxygen, nitrogen, carbon. These are all good examples of atoms that do not like to exceed the octet. And so they like to have 8 electrons around them. And when they have 8 electrons around them, they are good. So this is our structure for sulfur hexafluoride. Okay, can I get a thumbs up or something in the chat that, yes, you're good to go on, or a private message if, hey, I was a little bit confused by that. Okay. Do we feel better about drawing a molecule than we did 20 minutes ago? Can I get a yes or a thumbs up in the chat in response to that? Okay. To me, drawing molecules is kind of like it's something that whenever I first saw a molecule or first saw a picture, a Lewis structure, I was like, neat. I also can draw letters and put dots and lines connecting them. And then whenever someone was like, oh, well, here's how you draw it, I was like, again, I too can write letters and draw lines connecting letters to one another. And then whenever it was like, here's the process, I was like, oh, okay. So I'm taking, here, I'm gonna go ahead here. So I'm taking the information here, my list of valence electrons, and using that to draw a molecule. Okay, that makes a little bit more sense. Now, we'll move on from this one. We've got, we've got 2 more molecules to draw. BF3. So are these the diagrams we were supposed to do on activity 10? Yes. This is, all of this stuff is good activity 10 stuff. Okay. BF3. Oh man. Boron trifluoride. So that's 1 boron and 3 fluoride. What did we say about boron and the octet rule? Add it to the chat. It's an exception. It can have less than 8. How many do we see right there? Boron's got 3. I like boron. 1, 2, 3. There's boron. Fluorine. 1, 2, 3, 4, 5, 6, 7. Okay. So, yeah, it can have less than 8. So those are our 2 Lewis structures of the individual atoms. I like BF3 because, I mean, even without going through the process, I feel like lots of you guys can probably just kind of put it together. But let's go through our process just so we can have more practice on it. Boron rolls in with 3 valence electrons. So boron is 3 valence electrons. Here's my running total. Fluorine, well, there's 3 of them. Rolls in with 7. 3 times 7 is 21. I'll say 1, yeah, just to give myself a little bit more clear. 24. 24 valence electrons. My central atom, boron. My adjacent atoms, fluorine. 1, 2, 3. How many electrons have I drawn so far? Well, each one of those drawn 6. So 24 minus 6 is, yep, 18. Perfect. Thank you. Now, I'm going to switch colors just so I can jazz it up. I really don't have too many color options. I got primary colors and then some secondary colors. Rats. 2, 3, 4, 5, 6. Minus 6 gives us 12. Then around this fluorine. Coming around this fluorine, we got 6 electrons minus 6. We got 6 electrons left to draw. And then coming around the left corner, we got 1, 2, 3, 4, 5, 6 electrons minus 6 is 0. Is this structure good? I mean, I wouldn't say it's good. I'd say it's great. I'd say it's amazing. Do we have a complete octet for all of our fluorines? Yup. Do we have a complete octet for boron? Yes and no. Yes, because boron's happy, but no, because it doesn't need 8 electrons. It's happy with those 6 electrons. So, is this a good structure where I'm like, oh yeah, I'm feeling good? Yeah, it is. Okay. Again, this chart right here, we're going to use this for our last formula. Our last formula is none other than PCl5. Give me the name in the chat, and there's going to be another bonus point in it for you. And no Googling. Psh, that's right. Phosphorus pentachloride. Well done. Well done, folks. We're going to go back because we need our valence electrons. PCl. I'm going to throw that in parentheses 5. I'm going to throw that in parentheses 1. And okay. Some of these elements, you get so comfortable that you're just like, oh yeah, chlorine has 7. Now, before we proceed though, do we know anything about phosphorus that will be helpful whenever we're drawing this? Specifically with respect to the octet rule. Yes! 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 It's greedy! It can exceed the octet rule! Yes! Absolutely! Now, I got so pumped up about that, I forgot to actually remember the numbers that I was looking for. Chlorine's rolling in with 7 valence electrons. I know that. Phosphorus is bringing in 5. Okay. 5. Yep. 35. 40 valence electrons. Central atom, P. Cl. You get a Cl. You get a Cl. You get a Cl. You get a Cl. Makes a nice little starfish. Patrick Starfish from SpongeBob. Anyone watch SpongeBob? 2 of my kids do. I still don't really get it. I didn't get it when I was in high school when people watched it. I still don't really get it. But, it makes people happy, so I'm good with that. Okay, so boom, 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 boom. How many electrons is that? Or have I drawn? Sorry. And before I proceed, Well, I'll proceed and tell you this. 40 minus 10 is 30. This is one of the reasons that I like chemistry because you can say, hey, look what I drew. In what world can writing a letter and drawing a line be drawing? I don't know. But chemistry is that one of those worlds. How do we know if an element is greedy when it comes to the octet rule? Great question. What I want you guys to do is think about if it's, and actually, heck, I'll narrow it down. Phosphorus, sulfur, and chlorine are going to be the ones that you most often see as being able to exceed the octet rule. And basically, it's greedy. But also anything below these guys on the periodic table. Anything below or anything past phosphorus on the periodic table, it's going to be able to exceed the octet rule. Okay. So, like I said, this is why chemistry is great. Hey, look, I drew this. I mean, yeah, that's a pretty bold to be like, I drew this. I wrote a line. Okay, so we've got 30 electrons. 1, 2, 3, 4, 5, 6, minus 6. 24. 1, 2, 3, 4, 5, 6, minus 6. 18. 1, 2, 3, 4, 5, 6, minus 6. 12. 1, 2, 3, 4, 5, 6, minus 6 is 6. And then 1, 2, 3, 4, 5, 6, minus 6. 0. Okay. How are we feeling? Add it to the chat a Y or an emoji or something if you're like, I can draw Lewis structures. Okay. 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 Will it ever be unhappy? That's a great question. In the event that you draw a molecule and you don't end up with 0, then you got to circle back and do something where it's like, oh, I've got 2 extra electrons. What am I going to do with those? And that's actually what Monday's lecture is going to be about. And so we'll look at some molecules where you end up with 2 extra electrons. So what are you going to do with them? One of the things that, happy that you asked this, because one of the things that we will do in just a second that's important to recognize about this is molecules without lone pairs of electrons. Let me add a little bit of a detail though on the central atom. Okay, should we fill the electrons? Is that the question? Okay. Should we fill the electrons on each atom first, or can I do like 2 per atom until I think you could do 2 per. Yeah. I just honestly I fill up, yeah. Yeah, I think that you could do 2 per atom, and then if you run out, you're probably going to find maybe 1 or 2 atoms that you're like, oh, what do I do? Because there's 2 that are deficient. But if that's the case, then that's where you'd run into like adding a double bond or something like that. Um, but that's that. That's a great question though. Okay. Does anyone have any questions? I'm feeling good about this. I'm feeling good about the responses that I got. I feel like I got some really great questions, and from my vantage point, I think I answered all those questions. If you have any other questions though, please don't hesitate to hang around. It's 10:35. We've got class for the next little bit. I'm going to stop my recording though, and I'm just going to say as the last reminder, next week, Monday and Wednesday, it's going to be a pre-recorded lecture, and I'm going to send the announcement out like, hey, here's what it is, here's what you do. Um, if you have any issues with that, let me know, and I'm going to fix that. Um, and again, I'll have availability, office hour availability. Just shoot me an email and we can meet. And then, yeah. I'm gonna go ahead and stop my recording though.